Did you know that to harvest a single pineapple, an amount of waste weighing about 3 times the edible fruit itself is generated? Tens of millions of tons of pineapple leaves are left abandoned in the fields or burned every year, which can produce methane gas, a greenhouse gas that is dozens of times more harmful than CO2. However, as waste from non-biodegradable materials increasingly pushes the environmental crisis to new limits, pineapple byproducts have suddenly emerged as an extremely promising green material. So how, from an almost worthless agricultural byproduct, can modern industry create Piñayarn, Piñatex leather, and biological cleaners fermented from pineapple pulp? Today, join Agriculture Insight to discover how seemingly discarded pineapple leaves are transformed into a $1 million production chain that you might not know about. All will be revealed right now. With a production volume exceeding 29 million tons per year, pineapples have become one of the most traded fruits in the world, generating tens of billions of dollars for the global agricultural industry. Leading the race in recent years is Indonesia with a production of over 3 million tons, closely followed by the Philippines and the world's #1 pineapple export powerhouse, Costa Rica. However, unlike bananas, a crop famously known as almost zero waste, for every ton of pineapple harvested, up to 3 tons of leaves are wasted. To harvest, farmers must apply a strong force, twisting the fruit in a full circle to snap the fruit stalk off the parent stem. Meanwhile, the entire stem, base, and especially the dozens of sharp leaves, which account for about 75% of the plant's total biomass, remain firmly anchored in the ground. They do not pull up the whole plant right away because the root system still helps retain soil, reduce erosion, and prepare for the next planting season. Tens of millions of tons of pineapple leaves left behind in the fields not only decompose extremely slowly due to their high content of cellulose and plant sap, but burning them also releases toxic smoke and lung-damaging PM2.5 fine particulate matter. More dangerously, the piles of leaves decomposing under anaerobic conditions generate methane, a gas with a planet-warming potential dozens of times greater than that of CO2, turning pineapple waste into a burden no less significant than sugarcane bagasse, rice husks, or coffee grounds. While it cannot compete with lotus fiber in terms of rarity and high cost, pineapple leaf fiber boasts a high cellulose content, the compound that forms the sturdy structural framework of plants. Thanks to this, it is sturdy enough to be woven into fabric and made into bio-leather, yet light and abundant enough to become a large-scale industrial material. This potential has been officially elevated to a global scale by Dr. Carmen Hinojosa, who commercialized pineapple leaf fiber into bio-leather, while the people of the Philippines have been using it to weave fabric for hundreds of years. In the Philippines, the biomaterial innovation company Ananas Anam, founded by Dr. Carmen Hinojosa, has partnered with Dole Sunshine Company and more than 500 local farming households to turn a byproduct once destined for burning into a valuable source of raw materials. As soon as the ripe pineapples are cut off, hundreds of thousands of leaves, approximately 1.8 meters long, are harvested close to the base with sickles, bundled into bales, and quickly loaded onto trucks for transport to the workshop. This process requires the utmost urgency. If left for more than 48 hours, the inner leaf flesh will begin to ferment, weakening the structure and severely diminishing the quality of the precious cellulose fiber bundles. For the first time in the history of the pineapple industry, these leaves, once a disposal burden, now provide an additional 10 to 15% in extra income for farmers. At processing workshops, the journey of turning pineapple leaves into valuable materials begins with the most critical stage, fiber extraction. Each leaf is fed through a system of rollers, combined with high-speed mechanical scraper blades. Under continuous pressure and friction, the watery, sap-rich leaf flesh and soft tissues are gradually scraped away, exposing the cellulose fiber bundles deeply hidden along the leaf veins. In just a few seconds, leaves that would otherwise have been burned or left to rot are separated into two distinct material streams: the organic rich pomace, which can be utilized as fertilizer or biomass, and the most precious part, long, lightweight, yet high-tensile cellulose fiber bundles that form the exclusive foundation for the renowned Piñayarn and Piñatex. After being washed in water to prevent sap and acids from continuing to decompose, which would cause the fibers to yellow, become brittle, or even corrode and ruin the fibers over time, they are promptly transferred straight to drying racks for about 4 to 6 hours. At this exact moment, a natural transformation is officially triggered. Light and oxygen in the air break down the remaining chlorophyll on the fibers, gradually turning them from green to their characteristic ivory white. Not only that, the moisture inside the fibers is also reduced, bringing the cellulose bundles into a structurally stable state and making them ready for the next sophisticated transformation steps. However, the journey of these fiber bundles does not end at these rustic drying yards. After being baled, they cross thousands of kilometers to Barcelona, where the experts at Ananas Anam take over, refining each cellulose fiber to create sustainable materials that meet international standards. Upon arriving at the factory, the raw fiber bales are fed into a closed industrial centrifuge and washing system. This intensive treatment process completely removes any remaining microscopic impurities, dirt, or organic residues from the long journey, restoring the fibers to optimal purity before they enter the phase of deeper structural transformation into materials. To begin the opening phase, the tough pineapple fiber bundles, which can be up to 1 meter long, must be chopped and then passed through a coarse carding machine. Here, a rotating system covered with dense teeth continuously separates, detangles, and aligns the cellulose bundles in the same direction, turning them into a soft, fluffy, and uniform web of fibers. This is a mandatory step because if the long, tightly bound fiber bundles were left intact, they would easily wrap around the rollers, causing machine jams and significantly degrading the quality of the fibers in subsequent stages. From this point on, the material stream splits into two completely different production directions. One part is blended, stretched, and continuously twisted to form Piñayarn, a yarn used for weaving or knitting apparel fabrics. Meanwhile, a stitch bonding machine combines the processed fibers with thread made from cornstarch to create a durable sheet of material. This serves as the core base for making Piñatex, a leather alternative biomaterial made from pineapple leaves that offers a look and feel remarkably close to genuine leather. After being shaped, the material undergoes fully automated dyeing and drying. A resin derived from plants and petroleum is applied to provide color and enhance durability, followed by a heated roller that smooths the surface and cures the resin layer. The result is a leather alternative biomaterial that is tough, water-resistant, and highly abrasion-resistant, while remaining significantly lighter than animal leather. Arguably, the advent of Piñatex has opened up a new pathway for the sustainable materials industry, turning millions of tons of discarded pineapple leaves into valuable materials, thereby increasing farmers' income while easing the waste burden on the environment. This material has conquered numerous international brands such as Hugo Boss, Camper, H&M, and Paul Smith, where it is used to manufacture footwear, handbags, wallets, and various high-end fashion accessories. Notably, aside from the advantage of utilizing agricultural byproducts, Piñatex also features a smooth, firm surface that is easy to style, helping designers bring numerous creative ideas to life while pursuing environmental protection goals. So, are pineapple fiber products strong enough to change your choices, or do cotton, polyester, and animal leather remain your priority out of habit? What if the cleaning agent in your kitchen was safe enough to drink every day? Halfway across the world, the answer is taking shape right here in Asia with the story of Phua Biotech, a brand rooted in the name Fruit Warrior. Instead of leaving tons of pineapple peels and cores from canning factories to rot in landfills and generate methane, the team here has turned them into bottles of organic soap and dishwashing liquid. Inspired by a word-of-mouth method shared freely by a Buddhist nun and scientist, the production process of the Fruit Warrior, Phua, is meticulously carried out. All the discarded skin and core of young pineapples from canning factories are brought to the workshop and washed thoroughly to remove all impurities and dirt that could affect the fermentation process. Immediately afterward, the most crucial step of the entire procedure takes place: mixing. The pineapples are soaked in water and sugar according to a standard ratio, with sugar consumption reaching up to 2 tons per month. This mixture then enters an automated fermentation stage that lasts continuously for 3 full months. Catalyzed by lactic acid bacteria and yeast, sugar molecules are broken down, releasing an abundance of acids and special biological enzymes. Throughout this process, the team of workers must maintain daily stirring, otherwise the mixture is prone to molding, and the generated gases cannot escape in time, causing the fermentation tank to swell or even ruining the entire batch due to the invasion of harmful bacteria. By the second month, the appearance of a dense microbial mass is a sign that the fermentation batch has operated successfully. This mass is called a biofilm, the result of lactic acid bacteria, yeast, and other microorganisms during the metabolism of sugar and pineapples. After completion, the resulting liquid is blended with oils extracted from the stems and leaves of local agricultural plants to serve as the foundation for the natural cleaning product line. Meanwhile, the remaining solid residue is by no means wasted, but instead transformed into organic fertilizer for nearby farms. Before being approved for bottling, each product must pass tests for pH level, viscosity, biodegradability, and cleaning efficacy on food grease. Only when all criteria meet the requirements will the automatic filling line begin operation. Launched on the market at a price of just over $2 per bottle of dishwashing liquid, significantly cheaper than imported product lines, they have provided a benign cleaning solution that protects hand skin from eczema, while opening up the potential to replace toxic chemicals in the near future. Next time you see a pineapple, remember not to think of it as just a fruit. Behind it might be a shirt, a pair of shoes, a handbag, a bottle of dishwashing liquid, and an entire value chain that was previously almost invisible. And who knows, the next green revolution might not start in a laboratory, but right from the very things we used to call waste. So what other agricultural byproducts do you know of that are being neglected, but deserve a second life? Please share with us in the comments section. That just might be the topic for Agriculture Insight's next exploration journey. Surrounded by more than 7,500 kilometers of coastline and blessed with a tropical climate, India has become one of the world's largest coconut-producing nations. Every year, the country harvests more than 21.4 billion coconuts, supporting the livelihoods of more than 12 million people and creating an industry worth billions of dollars. But behind this enormous scale lies a paradox. A coconut consists of a high-value edible kernel and a fibrous husk that accounts for a large share of its total weight. After processing, around 35 to 45% of each coconut remains as husk and fiber, and nearly 70% of that material is still not effectively utilized, generating an enormous volume of waste every year. Meanwhile, more than 60% of India's population still lives in rural areas, where thousands of kilometers of roads are repeatedly damaged by monsoon rains, flooding, and weak soil conditions. After just a few rainy seasons, many roads begin to sink, erode, or wash away, making it extremely difficult to transport agricultural products and maintain connections between communities. The intersection of these two challenges gave rise to an entirely new breakthrough. Instead of treating coconut fiber as waste, Indian engineers transformed it into geotextile mats that reinforce weak soil and prevent erosion. Under the PMGSY-3 program alone, approximately 10 million square meters of coconut geotextiles were used to construct 1,674 kilometers of roads across 7 states, marking one of the largest large-scale applications of coconut fiber in the world. To understand how the fibrous layer surrounding a coconut became the foundation of sustainable roads and a billion-dollar industry, we must begin with the process of harvesting billions of coconuts every year. A mature coconut tree typically stands between 15 and 30 meters tall, equivalent to a 5 to 10-story building, with a nearly vertical, smooth trunk and no branches to hold onto. As a result, in many traditional coconut growing regions, farmers still climb directly up the trunk using only the grip of their feet, a rope looped around their ankles, or simple climbing aids. A single slip from a height of dozens of meters can cause severe injury or even cost a person their life. For shorter trees, farmers use sickles attached to bamboo poles or alloy handles measuring approximately 6 to 9 meters in length to cut down each cluster of coconuts from the ground. This method is safer and faster, but it is only effective for trees that have not yet grown too tall. Once the trees exceed that reach, climbing to the top remains virtually the only option. After the coconut clusters, each weighing dozens of kilograms, are brought down to the ground, the process of sorting and removing the fibrous husk officially begins. In many traditional coconut growing regions of India, this work is still performed entirely by hand. Workers drive a sharp steel spike measuring approximately 30 to 50 centimeters into the ground, then use their full body weight to force each coconut onto the spike, tearing the husk into several pieces. Even a skilled worker can separate only about 60 to 100 coconuts per hour using this method. Once separated from the coconut kernel, tons of coconut husks are collected into massive piles and transported to coconut fiber processing facilities across India. There, what was once considered agricultural waste begins its transformation into one of the world's most widely used natural geotechnical materials. After arriving at the processing facility, the enormous piles of coconut husks enter the most critical stage of the entire process, extracting the coconut fiber. Instead of soaking the husks in water for several months as in the traditional method, most modern factories in India use decorticator systems to fully mechanize the process. The coconut husks are continuously fed onto conveyor belts and transported into crushing machines. Inside, rotating shafts equipped with dozens of steel blades and high-speed hammers continuously compress, crush, and tear apart the tough outer husks. The impact force breaks down the bonding tissues between the fibers and the coconut pith, releasing long fiber bundles without damaging their natural structure. The crushed material then passes through a system of vibrating screens and air blowers for separation. The long fibers are retained, while the coconut pith, dust, and smaller debris are separated out. From 1 ton of coconut husks, a processing facility typically produces around 250 to 300 kilograms of coconut fiber. The remaining material consists primarily of coconut pith and moisture, all of which is later utilized to produce growing media or organic fertilizer. With the ability to retain water up to approximately 8 times its own weight, Along with excellent aeration and biodegradability, coconut pith is now widely used in vegetable farms, flower farms, and high-tech greenhouses around the world. The extracted fiber bundles still contain large amounts of dust and moisture. They are therefore thoroughly washed before being spread across drying yards covering thousands of square meters under natural sunlight. Throughout the drying process, workers continuously rake and turn the fibers to ensure moisture evaporates evenly while preventing the fibers from clumping together or developing mold. Only after the moisture content is reduced to 15 to 20% is the coconut fiber ready to move on to the heart of the entire coconut geotextile manufacturing process: carding and spinning. After reaching the required moisture level, the coconut fiber is fed into carding machines to remove short fibers, remaining dust, and align all the fibers in the same direction. This process makes the fiber bundles more uniform, softer, and ready for the spinning stage. Next, the fiber bundles pass through spinning machines, where multiple fine fibers are stretched and tightly twisted together into coir yarn of uniform thickness. The twisting speed and tension are continuously controlled to ensure the yarn has sufficient tensile strength to withstand heavy loads and outdoor conditions for many years. Every finished spool is inspected for diameter, tensile strength, and consistency before moving on to production. Only the spools that meet the required standards are transferred to the weaving system to produce geotextile mats used for soil reinforcement and erosion control. Using the coir yarn spools, the final stage begins on wide industrial weaving looms. Here, the yarns are woven perpendicular to one another in both the longitudinal and transverse directions, forming geotextile mats with mesh sizes and fiber densities carefully designed for specific applications. Depending on the project requirements, coconut fiber geotextiles typically weigh between approximately 400 and 900 grams per square meter, with a standard roll width of 2 meters and lengths ranging from 25 to 50 meters. These specifications determine the strength, soil retention capacity, and erosion resistance of each product. At this stage, these remarkable geotextile mats are ready to become natural reinforcement layers for roads and many other infrastructure projects. After the subgrade has been graded to the required design elevation, vibratory rollers and pneumatic tire rollers make multiple passes to compact the surface, creating a level, stable base that meets the specified density requirements before the reinforcement layer is installed. Once the roadbed has passed inspection, rolls of geogrid are transported to the construction site by truck, lifted into position using cranes or excavators, and distributed along the entire length of the construction corridor. Thanks to their relatively light weight, each roll can be pulled into position by several workers before being carefully aligned. The geotextile is then stretched to eliminate wrinkles and secured to the ground using steel stakes or bamboo stakes, typically driven into the soil at intervals of approximately 1 to 2 meters to prevent the mat from shifting during construction. At the joints, adjacent geotextile mats overlap by 20 to 30 centimeters, creating a continuous reinforcement layer across the entire road surface. Remarkably, constructing just 1 kilometer of rural road requires nearly 6,000 square meters of coconut fiber geotextiles. Once the entire geotextile system has been firmly secured, dump trucks begin placing the first foundation layer of sand, granular soil, or crushed stone over the surface. Instead of dumping the material into large piles, it is spread evenly in thin layers approximately 15 to 30 centimeters thick to avoid disturbing or damaging the coconut fiber geotextile beneath. Next, bulldozers and motor graders distribute the material evenly across the entire roadbed before multi-ton vibratory rollers compact it through multiple passes. Under the immense pressure, the soil and stone particles gradually fill the openings of the geotextile, creating a tightly bonded structure between the foundation layer and the natural ground beneath. Once the first foundation layer has been fully compacted and reaches the required design density, construction crews place the upper base layer using higher quality graded crushed stone. Finally, the road surface is completed with either asphalt concrete or cement concrete, depending on the requirements of each project. Throughout the lifespan of the road, the coconut fiber geotextile continues working beneath the pavement structure, reinforcing the foundation, reducing uneven settlement, and limiting erosion caused by rainwater. What makes this solution especially remarkable is that after approximately 3 to 5 years, once roadside vegetation has become well established and the soil has reached a stable condition, the coconut fiber gradually biodegrades, returning organic matter to the soil without leaving behind plastic waste like synthetic geotextiles. From a byproduct that was once discarded, coconut fiber has become the foundation of more than 1,500 kilometers of rural roads across India. This achievement has not only helped solve critical infrastructure challenges, but has also created a billion-dollar industry where agricultural waste is transformed into sustainable economic value. Amid the massive ocean currents of the North Pacific exists a region containing trillions of pieces of plastic swirling endlessly for decades, covering an area of approximately 1.6 million kilometer squares, or roughly 3 times the size of France. And the world does not have just one, but as many as 5 gigantic ocean garbage patches like this. These are not solid floating islands of trash as many people imagine, but rather a plastic soup dispersed across an enormous area where ocean currents continuously gather plastic from all over the world. But the real danger does not lie in the massive pieces of plastic visible to the naked eye. It lies in the process by which they are continuously broken down by sunlight, ocean waves, and friction over many years until they become nearly invisible microplastics. These particles then enter the marine food chain and eventually return to the human body itself. In ecological logic, every year of delay in cleanup means all future intervention efforts become more complicated and expensive. But humanity delayed that process for more than 7 decades, ever since petroleum-based plastics began exploding on a global scale in the mid-20th century. Scientists estimate that this region accounts for only about 1% of the world's ocean water, yet contains up to 7% of all floating surface microplastics globally, equivalent to around 1.8 trillion pieces of plastic with a total mass reaching 100,000 tons. For many decades, experts almost unanimously agreed that cleaning this area was impossible. Estimated costs reached tens of billions of dollars, and using traditional methods such as ships and nets, the process could take thousands of years. But right in the middle of what seemed like a hopeless situation, a bold idea began to emerge. Instead of chasing plastic across millions of square kilometers of ocean, humanity would let the ocean currents themselves concentrate the waste in order to capture and transport it into massive industrial processing systems before it permanently degrades into microplastics. It was an approach that went against conventional intuition, yet perfectly aligned with the way the ocean itself operates. And to turn that seemingly irrational idea into reality, a 16-year-old Dutch boy named Boyan Slat emerged with an approach completely different from every ocean cleaning method that had existed before. 1 year after a disappointing diving trip off the coast of Greece, where he saw more floating plastic bags than fish, in the fall of 2012, at the age of 18, Boyan Slat stepped onto the TEDx Delft stage with an 11-minute talk titled, "How the Oceans Can Clean Themselves."
However, I believe the Great Pacific Garbage Patch can completely clean itself
For months, Slat's seemingly naive question received almost no attention and gathered only around 2,000 views. But by February 2013, when technology and environmental media outlets began discovering it, everything changed almost overnight. Donations quickly started pouring in, forcing Slat to make the biggest decision of his life: continue pursuing his aerospace engineering degree or drop out of university to chase the ambition of cleaning the oceans. At the time, his bank account contained only around $300 in savings. Slat chose the ocean. Just days after the video went viral, the project received approximately $90,000 in donations. And by September 15, 2014, the total had reached $254,282, becoming the most successful non-profit crowdfunding campaign in history at that time. And from that moment on, in order to prove that the oceans could truly clean themselves, the Ocean Cleanup was officially born, with its first mission keeping millions of pounds of plastic stationary in the middle of the ocean. The Ocean Cleanup first had to solve an extremely complex physics problem: how to create a structure light enough to continuously float on the ocean surface, yet durable enough to withstand large waves, ultraviolet radiation, salt water, and mechanical stress for years in the open sea. The system's greatest distinction lay in its gigantic mechanical structure, designed as a U-shaped floating barrier approximately 600 meters long. To create this structure, the Ocean Cleanup used around 50 sections of high-density polyethylene pipe, each nearly 1.2 meters in diameter, a material commonly used in offshore oil and gas systems because of its corrosion resistance, impact durability, and ability to maintain stable buoyancy in harsh marine environments. Most importantly, the assembly joints were built using steel connectors, reinforced cables, and flexible linkages that allowed the entire structure to bend with the motion of the waves rather than resist them. Beneath the floating pipes, engineers installed a 3-meter-deep skirt made of technical fabric. This depth was carefully calculated to retain most plastic floating near the surface, while still allowing marine life to swim underneath, reducing the risk of harming the ecosystem. The operating principle of System 001 was based on a very small difference in movement speed between the system and the plastic waste. While floating plastic is pushed faster by wind and waves, Wilson generates greater hydrodynamic drag, causing it to move slightly slower and gradually funnel debris into the curved central section like a gigantic floating trap in the middle of the ocean. In September 2018, System 001, nicknamed Wilson, was officially towed out of San Francisco Bay to begin its first real-world test in the largest garbage patch on Earth. However, the system quickly revealed serious limitations. Unstable ocean currents and inconsistent drifting speeds prevented the system from keeping plastic concentrated inside the barrier, causing much of the debris to escape back into the ocean instead of remaining trapped for collection. By the end of 2018, an 18-meter section fractured due to material fatigue at welded connection points, forcing the system to be towed back to Hawaii after collecting only around 4,000 pounds of plastic in 4 months. The figure was far below initial expectations. As a result, System 001B was introduced in 2019, an upgraded version designed specifically to solve the problems that had caused Wilson to fail. Beneath the system, a parachute-style floating anchor approximately 6 meters long creates additional hydrodynamic drag, allowing the entire structure to move about 0.3 to 0.5 meters per second, slower than the floating plastic on the surface. This very small speed difference is enough for tens of thousands of plastic fragments to continuously accumulate in the central area, while retaining thousands of pounds of waste during each collection cycle. After around 6 to 8 weeks of operation at sea, The plastic accumulated in the center of the system is lifted onto the support vessel using industrial cranes. On the ship's deck, workers begin preliminary sorting of fishing nets, hard plastics, large containers, and organic contaminants before all the plastic is packed into containers and transported to recycling facilities. This process is extremely difficult because much of the plastic has drifted through the ocean for years, exposed to saltwater, UV radiation, and marine organisms that degrade and contaminate the material, making sorting and recycling far more complex than conventional land-based plastic waste. Its composition is also astonishing. Fishing nets account for 46% of the total mass, while between 75% and 86% of the plastic originates from offshore fishing activities. After more than 10 upgraded versions since System 001 Wilson, by 2025, the ocean cleanup had removed more than 25,000 tons of plastic waste from river systems and oceans worldwide, equivalent to the mass of tens of thousands of gigantic Labubu figures being pulled back out of the sea. But the ocean cleanup quickly realized that cleaning the oceans alone was not enough, because around 1,000 rivers, representing less than 1% of the world's river systems, are responsible for nearly 80% of the plastic continuously flowing into the oceans every year. Among them, Thailand, China, Indonesia, the Philippines, and Vietnam alone release as much ocean plastic as the rest of the world combined. This discovery changed the nature of the problem itself. Instead of focusing solely on cleaning up plastic that had already drifted into the ocean and dispersed across millions of square kilometers, the organization shifted toward a strategy of intercepting plastic at highly concentrated entry points, where river flow and geometry allow for far more efficient intervention in terms of energy and cost. From this logic, the interceptor system was developed as an automated river plastic collection platform. Each system is approximately 24 meters long, nearly 16 meters wide, and permanently anchored along riverbanks using heavy-duty piles and tension cable systems. Extending from the interceptor's main body, a floating barrier stretching dozens of meters is positioned diagonally along the direction of the current to continuously guide floating waste toward the central intake opening. As debris approaches the system, an automated conveyor belt approximately 1.5 meters wide begins operating, continuously lifting plastic from the water surface into the vessel. The entire system operates on solar energy, using around 32 solar panels installed on the roof to power the conveyor belts, sensors, and AI systems that monitor waste flow in real time. One of the most notable projects in the United States is Interceptor 007, deployed on the Los Angeles River, one of the most plastic-polluted urban rivers in America, where more than 220,000 pounds of waste were intercepted within the first months of operation before reaching the Pacific Ocean. But pulling millions of pounds of plastic back out of rivers and oceans was only the beginning. The next challenge was how to transform that chaotic mass of waste into reusable industrial raw materials on a massive scale. As soon as the material is brought back to land, the entire volume begins undergoing a careful sorting process based on polymer type, aging level, and recyclability. In reality, around 80% of the collected plastic has deteriorated and become contaminated to the point where it is no longer suitable for commercial recycling. This portion is typically processed through energy recovery systems or strictly controlled destruction methods to permanently remove it from the environment, instead of allowing it to continue breaking down into microplastics in the ocean. Only around 20% of the plastic remains stable enough to proceed into material regeneration lines. This mainly includes hard plastics, HDPE, polypropylene, and especially nylon fishing nets with lower levels of degradation. After being separated, the plastic continues through large high-pressure washing tanks to remove salt, sand, oil, and attached marine organisms before being fed into high-speed industrial shredders. Here, the material is cut into fragments several centimeters in size before continuing through polymer separation systems using optical sensors and float sink density sorting. The plastic that meets final quality standards is then melted at temperatures of approximately 180 to 280 degrees Celsius inside industrial extruders before being stretched into strands and cut into small recycled plastic pellets. Because of the extremely high costs of collection, transportation, and processing, ocean recycled plastic is often sold at prices up to 5 times higher than conventional recycled plastic, ranging from around $2,000 to more than $5,000 per ton, depending on material quality and purity. These plastic pellets are then sold back to manufacturers to produce sunglasses, packaging, electronic components, furniture, and many commercial products labeled as ocean recycled plastic. Some recycled ocean plastic has now even begun appearing in globally distributed commercial products. Coldplay once partnered to use plastic collected from rivers and oceans to produce recycled vinyl editions for one of their album releases, while Kia also partnered with the Ocean Cleanup to integrate recycled ocean plastic into next-generation automotive interior components. From a teenager standing in front of floating plastic bags in the Mediterranean, humanity has now, for the first time in history, begun truly addressing ocean pollution on a massive scale, proving that what was once considered impossible is sometimes simply a problem that has not yet been approached with the right way of thinking. After being collected and transported to the recycling facility, aluminum enters the sorting stage, a critical process that determines the quality of the entire recycling chain. At this point, large bales of scrap aluminum are placed onto conveyor belts and pass through a series of automated separation systems. Magnets are used to remove ferrous metals, while eddy current technology helps separate aluminum from plastics, glass, and other non-conductive materials. Beyond that, aluminum is further sorted in detail according to alloy types and intended applications, such as beverage cans, industrial aluminum, or construction materials. Even slight differences in metal composition can affect the quality of the final product, making precision at this stage extremely important. Once sorting is complete, the aluminum is effectively material cleaned and ready for the next stages of processing. After sorting, the aluminum is fed into high-capacity crushing systems, where cans and metal fragments are cut and broken down into thousands of smaller pieces. Under the force of intense cutting and impact, the original rigid structure is completely broken apart, turning the aluminum into uniform shreds that are easier to process. This step does more than simply reduce size. It plays a crucial role in optimizing the subsequent stages. Once the aluminum is shredded, its surface area increases significantly, allowing processing to occur faster, more efficiently, and with lower energy consumption. At the same time, the improved uniformity and particle size helps ensure better control over metal quality throughout the recycling process. After being shredded, the aluminum moves on to a deep cleaning stage to remove any remaining impurities. Although it has already been sorted, the metal surface may still carry layers of paint, ink, grease, and organic compounds left from its previous use. The aluminum pieces are passed through thermal and mechanical treatment systems, where high temperatures help break down and burn off paint, printing ink, and organic residues. At the same time, additional separation and filtration systems remove any remaining ash and fine particles, leaving the metal surface cleaner and more uniform. This is a particularly critical step as even a small amount of residual contamination can directly affect the quality of aluminum after melting. After impurities have been removed, the aluminum is transferred into industrial furnaces, where temperatures are raised to around 660 degrees Celsius, high enough to completely melt the metal. Under extreme heat, solid aluminum pieces begin to soften, deform, and gradually lose their original structure, merging into a glowing stream of liquid metal. During this process, aluminum is not simply melted, it also undergoes a form of refining. Lighter impurities such as residual paint, dust, and unwanted compounds rise to the surface as slag and are removed. At the same time, the high temperature fully breaks down old bonds, allowing the aluminum to return to a more uniform and purified state. Modern furnaces are designed to precisely control temperature and internal conditions, ensuring even melting, minimizing material loss, and preserving optimal quality. Once formed, the molten aluminum is kept in a stable state, ready for the next stages of production in the processing line. After reaching a molten and purified state, the liquid aluminum is transferred directly from the furnace into casting systems. Here, the glowing stream of metal is poured into large molds, where it begins the transition from liquid to solid. Depending on its intended use, aluminum can be cast into large ingots, thick slabs, or long billets, serving as intermediate raw materials for subsequent processing stages. This casting process requires strict control of both temperature and cooling rate. If cooling occurs too quickly or unevenly, the metal's internal structure may be compromised, leading to reduced quality. Conversely, when properly controlled, aluminum solidifies into a stable structure with the required strength and durability. As the molten metal gradually cools and hardens within the mold, aluminum once again takes shape, but this time, not as scattered fragments as before, but as uniform solid blocks of metal ready for the next stage of processing. After the aluminum has been poured into molds and begins to solidify, the metal blocks cannot be removed immediately. At this stage, they are cooled with water, typically through continuous external water spraying systems that rapidly reduce the temperature and stabilize the internal metal structure. The strong flow of water strikes the red-hot surface, producing thick clouds of steam, a clear sign that the cooling process is actively underway. Once the temperature drops to a safe level and the aluminum has fully solidified, industrial cranes come into operation. Massive cylindrical aluminum blocks, weighing several tons, are securely gripped by specialized mechanical clamps and carefully lifted out of the molds with high precision before being placed onto the factory floor. This entire process requires close coordination between machinery and technicians to ensure the blocks are not deformed or damaged during handling. At this point, the surface of the ingot still retains characteristic wave-like textures formed during solidification, while internal heat has not yet fully dissipated, meaning they must continue to be carefully monitored and controlled before moving on to the next stage. After cooling, aluminum slabs are fed into the rolling line, one of the most critical stages that directly determines the quality of the final cans. Here, the aluminum passes through a series of high-strength steel rollers where it is subjected to extreme pressure to gradually reduce its thickness. From blocks tens of centimeters thick, the aluminum is rolled through multiple stages, with each pass only slightly reducing thickness to avoid damaging the metal's internal structure. This process typically combines both hot rolling and cold rolling. In the initial stage, aluminum is rolled while still at high temperature, making it easier to deform and requiring less force. It then continues through cold rolling at lower temperatures, which increases strength, hardness, and improves surface finish. Between rolling cycles, annealing treatments are applied to restore the metal's ductility after it has hardened due to deformation. The result of the entire process is extremely thin aluminum sheets, typically around 0.2 to 0.3 millimeters thick for beverage cans, while still maintaining high strength, pressure resistance, and uniformity. These sheets are then wound into large coils, weighing up to tens of tons, and transported directly to production lines, where they will be stamped and shaped into finished cans. From these thin aluminum coils, the material enters high-speed stamping lines, where it is cut into circular discs and then deep drawn into the initial cup shape. From there, these aluminum cups are further stretched and thinned into can bodies through a drawing and ironing process, reducing wall thickness while maintaining the necessary strength.